So, as Shreyas mentioned, today's lecture is on optimization. And, all right. So, before I dig in, I'll say that this is kind of an odd topic to teach without discussing calculus. But as we mentioned early on, we want to make this course accessible to a broad range of audiences. And that means we want to offer it without using without requiring the knowledge of calculus. So for those of you that have had calculus, you might recognize some of the terms I'm using. For those of you that haven't had calculus, some of the terms, some of the concepts might be a little bit over your head, but we want to get the main ideas of how these optimization algorithms work so that you can apply them in practice. And most of these algorithms are already coded in Python packages like scikit-learn that Shreyas introduced last week. So let's dig in. Shreyas presented a slide almost exactly like this last week, where we discussed the machine learning kind of what we'll call it the pipeline. We collect the data, we import it into whatever language we're using. We split the data into a training set and a testing set. More about that in a couple weeks. And then we train the model. So this is the process of finding parameters which optimize our cost function. So the cost function was something we introduced last week. Essentially, it just measures how well our parameters fit the data given the model that we're using. So in the case of simple linear regression, this was finding the best values for M and B, that slope and intercept, which minimize the mean squared error. And of course, you'll probably remember that we stopped using the variables M and B and started using theta1 for M and theta0 for B. And I'll go back to that starting in the next slide. And then after that, we test the model. So again, this was using a data set that was not part of training to measure how well the model does. But tonight, we're really talking about step 3 here, and that's training the model. Finding the optimal parameters. So as I mentioned, we seek to minimize what we're calling the cost function. Again, it's really important that we understand what this cost function is. The cost function, which we'll denote by J, is a function of our parameters theta, and it measures essentially how well our model fits our data. So from linear regression, we remember that J of theta was equal to 1 over n times the sum of the squares of all the errors. So if we expand that a little bit, that's the observed y value versus minus our predicted y value squared. And if we want to be really explicit, it's just the observed y value minus this linear term theta0 plus theta1 xi. So again, in non-technical terms, we need to find the parameters for the model which provide us the best fit. So essentially what we need to do is find a minimum of this, this cost function. So in 1D, our cost function might look something like this. So this red curve. And you see that if we just look at this curve, it's really easy to find the minimum. It's right there at the bottom where that blue arrow is pointing. Unfortunately, it's not always this easy. First of all, we can only really visualize this cost function when we either have 1 or 2 input variables, so 1 or 2 parameters. This is an example with 1 parameter, so the parameter values on the x-axis, and the cost function is on the y-axis. So we can find that minimum visually, but that's not very technical. And as soon as we get to 3 or more parameters, we're not going to be able to visualize this very easily. So we need a mathematical recipe for finding that minimum. So let's go back to one of the examples from last week, and that's multiple linear regression. So multiple linear regression is the extension of simple linear regression, where we have multiple explanatory variables. Sometimes these are called independent variables. We'll call them explanatory today. And the multiple linear regression model takes the form that you see here. The ith test score is equal to some constant, theta 0, plus theta 1 times the number of hours a student studied, plus theta 2 times their score on the homework. So this is what we're trying to model today. So how well does a student do on their test based on the hours they studied and the score on their homework? So we can look at a few examples here. This is a made-up data set, but it makes sense. In general, maybe when you study more, you get a better test score, and when you do better on the homework, you get a better test score. So just to reiterate, x sub I 0 refers to the number of hours that student I studied for the test. So that's student I, and x0 refers to the first feature, hour studied, and x sub I 1 refers to the score on homework for student I. So for example, x sub 0, well, x sub 1, 1 would be the score that student 1 got on their homework, which would be 88. S sub 4, 1 would be 100 because student 4 got 100 on their homework. And we're trying to predict their test score. So in order to plot this cost function, the cost here is a function of 3 parameters now, theta 0, theta 1, and theta 2. And we would need 4 dimensions to be able to plot this. So we can't do that. And still, this is one of the most simple algorithms in machine learning. We haven't even started discussing something more complex like artificial neural networks. And we already have 3 parameters that we have no hope for visualizing. So we need an algorithm that helps us find the minimum in a more generic setting that doesn't require visualization. So how do we do that? And the way we do this is called gradient descent. So I need to minimize the screen here. All right. And essentially, how gradient descent works is it's pretty simple. So let's say we start at this point here. Can you see where my mouse is on the screen?
I can't really see it.
Okay, let me see if I can.
Oh yeah, I can see it now, I think.
Here, so let me see.
Oh yeah, I see it. Yeah, I see it now.
So let's begin at this point. We shouldn't. I don't know if I can use a different color. Oh, sorry, I'm a little new to Zoom. We'll try the spotlight here. All right, so this looks like a laser pointer. So we'll begin at this point. This point is our first estimate of the optimal parameters for our model. And essentially, the gradient descent algorithm asks, which direction is downhill? So in this case, looking at this function, if we were to move the parameter to the right, it would go uphill. And if we were to go left, we would travel downhill. So gradient descent says, let's follow this function downhill. So we'll move a short distance from point 1 to point 2. Again, we look and say which direction is downhill, and we find again that it's to the left. So we move to the next point, and so on, until eventually it settles in at this minimum value where the gradient is 0. And that means that if we were to move left or move right, we'd be essentially going uphill in both directions. So that's not a very technical way to say this. Again, we're trying to discuss this without calculus. But at this point at the bottom, in 1D, we'd call this the derivative. The derivative is 0. And in multiple dimensions, we'd say that the gradient is 0. So we just repeat this process, starting from our initial point, taking one step at a time. So these are our first parameters. We'll call those theta 0, then theta 1, then theta 2, then theta 3, theta 4, and so on until we finally converge on this point at the bottom of the hill. All right, easy enough. So here's a question, does it work? Well, the answer is kind of yes and kind of no. Let me erase some of the drawing I had done on the previous slide. So it depends what our function looks like. If our cost function looks like this big U shape, well, that's great. We only have one minimum value. We can see it here. And whether we start over here on the left or start over here on the right, either way, when we head downhill, we'll find this minimum. But that might not be true if our cost function has a little bit more shape to it. If it has what we call a local minima and a global minima. So the global minimum is really the value where the cost function attains its minimum everywhere. But a local minimum is a point at which the function value is lower than the function value for all points around it. So if I were to kind of look only at this tiny region around the laser pointer here, that point is lower than all other points nearby, so it would be considered a local minimum. This point over here is called a global minimum because it is lower than all other points on the cost function. So linear regression, luckily, gives us a cost function that looks like this one on the left, in which there's only one minimum, and it's pretty easy to find generally. However, there are other algorithms like artificial neural networks, which might have many local minima, and it might be difficult to actually find the global minimum, because if we were to start with parameters, say here, and we were to look in the downhill direction, it would want us to move to the right. So we'd follow this path down, and we'd end up getting stuck over here. So this is maybe a decent model, but it's not nearly as good as the model over here in which the parameters fall at the global minimum. For those of you that have taken linear algebra, you may be aware of an alternative method for finding the set of parameters in linear regression. There's a more direct method that's available, but gradient descent is also a perfectly valid method for finding these optimal parameters.
Dr. Willett, can I interject with just a quick question?
Sure.
And maybe you guys talked about this last week, but when you talk about linear regression, whether it's simple or multiple linear regression, do you usually have a heuristic or frame in mind in terms of how many data points you need in order to assume that, that you have any reasonable model? And if you're using, technology, when do you get to approaching infinite number of data set values that you assume that you've got a good solution?
Yeah, so that's a great question, and it's actually going to be an aspect of Shreyas or Shraman's lecture in a couple weeks when we talk about overfitting versus underfitting, and understanding that if we have too complex of a model for the number of data points that we have, the model has the capability to essentially memorize the data points, and it won't work well when we apply it to new data points that we haven't seen before. So to answer Mr. Lobler's question directly, it's really difficult to say. It really depends on your setting. For simple linear regression, having 20 or 30 data points is probably enough. If you have 20 explanatory variables, then that number becomes a lot higher. You'd probably want 1,000 or 10,000 data points in order to try to fit 20 different parameters using the linear regression model.
Great, thank you.
That answer your question?
Well, yes, yeah. The reason I brought it up is because oftentimes when I introduce linear regression to statistics students, they far too often think that they can actually develop a good model when they have far too few data points, and so that's one of the reasons that I asked. But
It's a very good question and is a big topic in machine learning. So we'll talk more about that in future lectures.
Yeah, we'll talk about that in lecture 7, I believe.
So there's another thing that we need to discuss today, and that is a concept called computational complexity. So each one of these algorithms follows some set of math algorithms, some set of math steps, a set of logic that take it from the initial guess for the parameters and end up with our final solution. And the more complex an algorithm is, basically means the longer you'll wait in front of your computer for results. And now this might not seem like a big deal because a lot of the problems that you've maybe seen in the past haven't been very big. But when we start talking about machine learning, and as Mr. Lobler just alluded to, we might have hundreds or thousands or millions or billions of data points. And as the number of data points increases, the runtime for these algorithms increases dramatically as well. So let's try to figure out how computationally complex the gradient descent algorithm is for linear regression. So let's look at our cost function. And we showed this on the first slide. But again, j of theta is equal to 1 over n times the sum from I equals 1 to n of y sub I minus theta 0 plus theta 1 times x sub I, and that whole quantity is squared. So let's say, how much does it cost to evaluate the cost function? So this cost here in parentheses is a computational cost. How many operations do we have to do? And you could think about this yourself, right? If I had to sum up 100 numbers, how long would that take me? Well, maybe I can sum 2 numbers every second. So it would take me about 100 seconds to add up this list. The same is true for the computer, but it does it much, much faster. So we need to think about all the math operations we need in order to compute this summation. And let's break it down. So let's first evaluate the expression in the innermost parentheses. So right here, this theta 0 plus theta 1 times xi. How many math operations does it take? Well, the first thing we have to do is we need to multiply 2 numbers. So we multiply theta 1 times x sub I, and then we add that to theta 0. So far we've had 1 multiplication, theta 1 times theta xi, and 1 addition, theta 0 plus the product of theta 1 and theta xi. Okay, now if we evaluate the expression inside the brackets, so these square brackets here, we have y sub I minus the quantity we just computed. So that's another addition. When analyzing algorithms, we'll pretend that addition and subtraction are essentially the same thing, since for the computer, a minus b is the same as a plus negative b. These operations are really exactly the same. And the same is true about multiplication and division. So we'll consider all division operations multiplication as well. And that might not be entirely true, but it's good enough for our estimation purposes. All right, so far we've evaluated everything inside these brackets, and we've counted 1 multiplication, 1 addition, and then 1 more addition. And then we have to square this term. So we have to take the quantity that's inside the brackets and multiply it by itself. So that's 1 more multiplication. So we're at 2 multiplications and 2 additions. And we have to sum this n times. So for every observation, we need to compute these 2 multiplications and 2 additions. We have to do that n times, so 2 times n for each of those. And since there's n terms in this sum, we need to do essentially we have to add up n things, so n more n more additions. And then we need to multiply by this factor out front. So what does that look like in total? So we have 2 times n plus 1 multiplications, and we have 2 times n plus n minus 1 additions. So that simplifies to 3 times n minus 1. And recall that n here is the number of points in our data set. So if n is big, we can kind of ignore this plus 1 and minus 1. We'd have about 2 times n multiplications and 3 times n additions. So if we, let's just say, had 1 million data points, we'd need to multiply 2 million numbers together and add 2 million numbers together in order to compute the cost function just one time. And it turns out that for this algorithm, computing the gradient basically costs the same thing. So it's important to realize this because we might choose our algorithms based on how much they cost relative to how good of a solution they provide. But what we've seen is for this most simple ML algorithm, linear regression, it could get quite expensive just to compute the cost function when we have a lot of data points. So with that in mind, we might ask the question, well, how do we make gradient descent more affordable? Because if we need to take 100 steps, so recall, I'm going to go back a few slides. Here I've just shown maybe 7 steps. Each time we take a step, we need to compute the cost and the gradient. So we repeat that 1, 2, 3, 4, 5, 6, 7 times. And if we were, if our data set had 1 million elements in it, that would mean we'd be doing about 14 million multiplications and 21 million additions. That's quite expensive. Again, the computer's really fast, so it can do it quite quickly. But is there a way to make this more affordable? And it turns out there is. And what we do is we can take some subset of the points. We'll call this a batch of points. And we could compute the function just using, say, the yellow points in this picture. And this will be an estimate of the cost. It's not going to be exact. But if we pick these points randomly, it should do a pretty good job. And again, we're not trying to be perfect. We're just trying to get a good estimate of the cost. And we'll use those same points to get an estimate of the gradient. And then in the next iteration, we might take all the blue points and use those to compute the cost and the gradient. And then in the next iteration, we might take all the black points and use those to compute the cost and the gradient. When we use just the yellow points, or blue or black for that matter, we can reduce the cost by a factor of 3, and it's still very accurate. So the concept is using small batches of our data allows us to compute a good estimate to our cost function and our gradient using significantly less computation. This is one of many modifications to gradient descent that improves its performance and can be referred to as MiniBatch gradient descent. There's also another version called stochastic gradient descent, which essentially just picks points at random every step and uses those to compute the gradient and the cost function. So we've just discussed, we've noted that gradient descent can be expensive, but there are ways to mitigate that cost. There's also one other issue. What happens if we take too big of steps? So let's look at this example on the right-hand side. If I look at this point here, and I say, which direction is downhill? Is it left or right? Well, the answer is clearly to the right. But what we haven't discussed is how far we step to the right. And what I've alluded to so far is that we'd step basically proportional to the gradient. But the gradient might be really big, and it might cause us to actually overshoot the minimum. So it's possible that if we started here and took a big step to the right, we'd end up actually further away from the minimum than when we started. And then at the next step, the same thing could happen, and we might shoot off to this third point, which is even further away. This can repeat, and we want to fix this, and we do that by adding a learning rate. And we call this learning rate the Greek letter eta. That's ETA. If you are looking for it in Microsoft Word's equation editor, you would search by ETA. So our new iteration would be theta n plus 1. So our new parameters are equal to our old parameters plus eta times the gradient. And eta is chosen to be less than 1. So commonly, you might see eta equals 0.01, 1/100th. That's a very common value for eta, or maybe 1/1000th. Essentially, what it's doing is it's forcing us to take much smaller steps, but that ensures that we don't overstep our minimum. And it has a tendency to increase the convergence rate when it's done correctly. It prevents us from bouncing back and forth and back and forth. So someone last week had asked if we'll only be using Python, and I pointed out that the answer to that was no. We also discussed that we would use Octave or MATLAB for some of the demos. So for tonight's demo, I'm going to show how you might optimize the linear regression cost function with the SAT scores data set that Shreyas introduced last week using gradient descent. And later this week, I will try to post the same code using Python. So, and I'll make time for questions in a few minutes. So let me share my Octave window. Shreyas, can you see my window now?
I can see it.
Okay, great. So this is Octave. This is the Octave GUI. As we've mentioned in the past, Octave is an open source version of MATLAB. It doesn't necessarily have all the same features, but it has most of them. But the nice thing is it's free, where a MATLAB license might cost a couple $1,000s. It might be a little cheaper for students, but still it's not free. So as I said, let's try to predict SAT math scores based on the SAT reading scores and SAT writing scores, the same way we did last week, and also the number of students that took the test at the same time as the student. So when Shreyas demoed this last week, basically he had a workflow that looked like reading the data in. So we do the same thing in Octave. We can use this CSV read function to load the file. Octave, unfortunately, doesn't have the nice feature that Pandas does that automatically creates a table. There might be a fancier way to do this, but I don't want to get into that tonight. So we need to drop the first row of data. Those are just the text column names. So I'm saying I want all the data, and the way to read this is I want it from row 2 to the end of the matrix, and I want all of the columns. So this colon basically says I want all of the columns. And we can look at a small sample of the data as well. So let me run this, and it's going to run a little bit too much, but that's okay. We can go back. All right, so oh no, I accidentally closed Octave. I'm sorry, guys. Give me 1 second to boot that back up. I apologize. This isn't my normal computer. taking a couple extra seconds to boot up.
May I ask a question in the interim?
Absolutely.
Shreyas, have you talked about, for those who might miss a class or if they're trying to catch back up or review, where you have posting of the recorded previous sessions and that information? Did you share that in previous classes?
Yeah. Yeah.
Okay.
So essentially what we're going to do is we have a Google Classroom and we'll post the code to Google Classroom in the chat. And that's where we'll post a link to our recording.
Okay.
So we recommend you to join our Google Classroom. So if you want to view it.
Yeah, and we'll communicate about that later. I just want to make sure that everybody knew that for those who might miss a class here and there in the future. So.
Oh, okay.
All right, we're almost there. I apologize for the short delay.
I'll ask one more question. Shreyas, for those who might not be familiar with calculus, how would you summarize quickly what is calculus for those who just see it as a foreign math subject they haven't taken yet?
Okay, so in regards to optimization, one thing that so there's pretty much two big branches of calculus: differentiation and integration. So in regards to optimization, we usually think about differentiation as differentiation usually the big field of calculus that we're concerned in with optimization. And essentially, what differentiation is if you think of a function, it's essentially, I guess, the slope. It's essentially I guess it's essentially like the slope of the tangent line at each point. It's quite difficult to explain non-technically, but I'm sure that if someone really wants to learn derivatives, they could probably just Google Google derivatives and learn the basics in just a couple of days if they wanted to.
I appreciate that you mentioned the two big branches, and really at the heart of derivatives is thinking about rates of change and really instantaneous rates of change. But no, that's good, and they can get into integration later. So I was just filling the time as Dr. Willett was getting set up.
Yep. Okay. Are you set up yet, Dr. Willett?
Yep. Can you see my screen now?
Yeah. Yeah, I can see your screen. Yeah.
All right, so let me run this again. I apologize for the little mishap there. All right, so remember what we've done so far is we've loaded the data. I've trimmed the first row of the data off, and now we want to look at a little example of the data. So essentially, this is what it looks like. It's broken up into two lines here. I think I might be able to take a look directly. I'm having a little trouble using Octave on my Mac tonight, but it works very well on my Windows machine. So here are the first 5 rows. So in the first observation, 29 students took the SATs. The students scored a 355 on the reading section, a 363 on the math section, and a 404 on the writing.
Dr. Willard?
Yep.
Dr. Willard? We can't see your screen.
Oh, you can't?
No. We can only see just the top portion of your screen. We can't see the actual code. Yep, we can see it now.
This works? Shreyas, can you see it now? Sorry.
We can see, yeah, I can see it at least. Okay. Can everyone else see it? Okay.
There's always technical difficulties. So sorry about that, guys. All right, so now that we've loaded the data, we can select the columns we want as our explanatory variables. So here we'll select columns 1, 2, and 4. That's the student count, the reading score, and the writing score. And we'll assign that to the variable x. And then we'll select our dependent variable. That's the math score. We do that by selecting column 3 from the data. And here we can see essentially what X and Y look like. And then what we've done is I've asked MATLAB to solve this linear regression problem using both gradient descent and a different methodology. So this direct method is a method that you'd learn about in linear algebra, and compare how much time it takes each of those methods to solve it. And you'll see that the two methods came up with the same solution. So here are the parameters from gradient descent, and here are the parameters from the direct method. They vary a little bit in maybe the first decimal place or beyond, but essentially they provide the exact same model. And if we had run gradient descent a little bit longer, they would have ended up being exactly the same. But gradient descent took about 2.5 seconds, and the direct solve took 5/10,000ths of a second. So much, much quicker. So in general, as I mentioned during the lecture, linear algebra techniques allow us to solve this problem directly, but gradient descent works as well, and this is a good application for demonstrating gradient descent. So if we want to look at the gradient descent code specifically, it's actually quite simple. So what we need here is a couple of functions. We need a cost function. So we can compute the cost. All we need is x, y, and theta. So again, our parameters. And we can use some linear algebra to compute this summation actually in very little code. So we can compute the number of observations by looking at the size of y. So that's just the number of elements in the vector y. We can compute the error via this matrix multiplication. And then we can compute the cost by multiplying these error vectors together and summing them and dividing by n. So that's maybe a little technically wishy-washy, but since we haven't discussed some of these linear algebra concepts, I don't want to get into all of the details. And then we also have a gradient function. And you can see, again, I can write this gradient function in about 3 lines of code. Again, computing the length of the vector y, computing the error, and then doing a little bit of linear algebra. So once I've defined the cost function and the cost gradient, here's my main linear regression gradient descent loop, essentially. We pick some initial values for theta. Here I've just chosen to use a random number generator to get that initial iterate. For some algorithms, there might be a slightly better way to do that, but that's kind of beyond the scope of this class. We'll compute the initial cost. So at our first estimate of theta, what is our cost function? And at our initial estimate of theta, what is the gradient? And then at each step, so some of this is just bookkeeping, me keeping some information around so I can make a couple plots. We compute eta, so this is a slightly more fancy way of doing it to try to make sure that we take the biggest step we can, but not too big of a step necessarily. And then we update theta, just as I described in the PowerPoint. So the new theta is equal to the old theta minus eta times the gradient. And then we update the cost value, we update theta, we update the gradient, and then we go back to the top of the loop. And we'll keep iterating here until the gradient is very, very small. So depending on how small I make this, kind of dictates how long it takes to run. And if we look at this figure, this second blue curve here at the bottom shows what the gradient, the norm of the gradient looks like over time. So after about 10,000 iterations, the gradient becomes about 1e to the minus 4, so that's 1 over 10,000 in terms of its norm. So at first,
Jeff, I think your screen's frozen.
unfortunately, when I switch windows within Octave, it doesn't seem to like it. Can you see my plot now?
Yes.
All right, sorry about the technical difficulties, guys. So as I mentioned, at the beginning, the norm of the gradient was around 1,000, but after about 10 iterations, it's dropped to below 100. After 100 iterations, it's about 3 or 4, and after around 8 or 9,000 iterations, the norm of the gradient has dropped below 1 over 10,000, which essentially means the gradient is becoming very, very small, and we're very close to a solution. So with that, I think we'll go back. I apologize that we haven't had a great experience with Octave tonight. I'll go back to the lecture slides here. This went a lot more smoothly with Python, and I have to say, Python is my tool of choice. All right, so let me share. So with that, I'll conclude the demo for tonight. Again, apologies for being a little bit messy. We're all learning throughout this experience. And I'll post the code to our Google Classroom so you can dig in a little bit further. But at this point, feel free to unmute and ask questions in the chat, or ask questions in the Google Classroom later on. Do we have any questions?
Dr. Willett, can I start with one?
Absolutely.
So you were highlighting the difference in time it took for the two different processes to actually come to a solution. How long did it take you in Octave to actually go through and write that code to run that?
Honestly, so in Octave, it's very easy to do linear algebra. It's actually one of the reasons why Octave or MATLAB is used so much. It's great for prototyping algorithms. So I could essentially write the linear regression code in about 1 line once my variables have been defined. Now, again, that comes with some experience for having done it for a while. But the gradient descent is only about 15 lines. I guess you have to include the definitions of the functions, but that still is only maybe another 5 lines each. So we're talking about a total of 30 lines of code. So it depends how fast you code, but something you could do in a half an hour or an hour, again, if you knew calculus.
Oh, great. Well, and that also highlights the fact that the more versed you are in fields of mathematics, then the more apt you are to be able to code.
Yep. So I see a question from Kevin in the chat. How do you avoid falling into local minima in gradient descent? So that's a great question. It's probably a little bit beyond the scope of this course, but there are a variety of ways that algorithms handle this. You can change the size of your step and hope that you step over small local minima. That's not a great solution because as you saw in the image that I shared early on, those minima might be quite big and you'll get stuck in them either way. Another way to do it is by picking several different starting points and optimizing from each starting point independently. That's also not a great solution because if I want to start from 5 different points, that essentially means I need to run the algorithm 5 times, and that's 5 times the amount of time you're going to spend in front of your computer. So I can point to some literature after class that might discuss this in more depth, but I think it's a little beyond the level we're trying to discuss here today. I see another question. In terms of machine learning algorithms, would Octave be better than Python as a programming language? That's a very tough question. I say that Octave is much better for prototyping, just because it's very easy to inspect your variables, and it's also really easy to do linear algebra, so that's matrix multiplications, compute norms. Those are all very easy built-in things to do, whereas in Python, you need to load some packages and libraries that help you out with that, and it might not be quite as straightforward. So it's really a matter of preference, and it depends on what you're doing. Python's going to be faster in most cases, especially when you consider that Python has the capability of using advanced hardware like graphical processing units for deep learning. I don't know that that's supported in Octave. It is supported in MATLAB, but again, that would require a proprietary license. So if you know both, it's great. If you know just one or the other, that's great too. But I wouldn't worry about trying to learn both right now. So we have another question, and how do we know which point is the global minima if the graph is not a parabola? And that's another question that kind of relates to Kevin's question. We cannot know if we found a global minima or a local minima in general. So if we find a point and the gradient of that point is 0, that gives us no guarantee that it's a global minima. All it tells us is it's a local minima, and it could be a global minima. So really, like I said, there's not a great way to know, and that's one of the things that makes this challenging. You can develop some intuition to figure out if maybe the model you have isn't representing your data as well as it should be, or it has the ability to, given the underlying structure of the model and the parameters you're using. So unfortunately, I don't have a great answer for you there. It's more a matter of maybe trying a couple of different initial iterates and seeing if they all converge to the same solution. So I saw one comment here that the number of extrema of a function is n-1. In general, the functions that we're dealing with will not be polynomials. As we move to artificial neural networks, these are going to be highly nonlinear functions which don't have a nice theory like that. So we cannot guarantee that there's only a specific number of extrema. But if you're doing polynomial optimization, you can use those extra facts. Any more questions? Again, thank you everyone for bearing with me tonight through the technical difficulties. If you have more questions, feel free to post them in the Google Classroom.